All right, let's dive into the fascinating world of physics, shall we? So here's the deal. The Standard Model is a pretty big deal in the universe of particle physics. But hold on tight, it doesn't quite cover gravity, and there are still loads of questions floating around out there, like what the heck is dark matter? This really puts a spotlight on how we need a deeper, more comprehensive theory to get a grip on the universe. Crazy, right? Now let's talk about the Higgs field and the Higgs boson. These two were game changers, giving us a peek into how particles get their mass. But here's the kicker. Their discovery showed us that the Standard Model is a bit like an iceberg. There's a lot more beneath the surface, especially when it comes to the mysterious stuff going on in the universe. It's like we're just scratching the surface of understanding particle interactions, and there's so much more to uncover. As cool as the Standard Model is, it's not all sunshine and rainbows. Its parameters? Totally arbitrary. It leaves physicists scratching their heads over some mind-boggling phenomena, like the mass of neutrinos and vacuum energy. This ongoing quest for deeper answers shows just how driven scientists are to push the boundaries of theoretical physics and unlock the universe's secrets. Talk about determination. And here's where the idea of spontaneous symmetry breaking comes into play. This concept is massive in how particles gain mass while keeping the gauge symmetry intact. It's like having a hidden secret, the universe's way of maintaining harmony while letting particles strut their stuff with mass. Simply fascinating. Ever wonder how particles get their mass, but some, like photons, stay light as a feather? The Higgs mechanism explains this by suggesting a field that gives mass to particles while leaving others free and floating. It's mind-bending and shows us just how complicated the whole mass generation gig really is. Now, let's think bigger for a second. The mass of particles isn't just a nerdy concept. It actually impacts atomic structure, star formation, and even how planets come to be. It's like the universe has its own recipe book, and mass is a crucial ingredient in the cosmic kitchen. The journey to find the Higgs boson was no walk in the park. It took some serious tech and teamwork, culminating in the epic creation of the Large Hadron Collider at CERN, where they smashed particles together at insane energies. This was a monumental project that required the best minds and resources coming together. Talk about teamwork making the dream work. So, guess what? When they finally found the Higgs boson, it was a massive validation for the Standard Model, and it even earned a Nobel Prize. But hold on, it also opened up a can of worms, revealing that there are still big gaps in our understanding of the universe. It's like adding a new chapter to a book that still leaves a ton of questions unanswered. Despite that huge find, the universe still has a lot of mysteries left, especially when it comes to dark matter and dark energy. This keeps the flame of discovery alive, reminding us that research is never really done. There's always more to dig into. Now, let's take a moment to appreciate the journey of Peter Higgs himself. He faced a mountain of skepticism and rejection, but did he throw in the towel? Nope. He pressed on, producing detailed mathematical papers to back up his theories. His cool demeanor helped him ride out the waves of criticism from the scientific arena. Now that's what we call perseverance. Fast forward to 2012, and the discovery of the Higgs boson became a landmark moment in particle physics. It was like the cherry on top of a giant scientific sundae, confirming decades of theories while showcasing the sheer power of collaboration and tech in research. Honestly, it was a total win for science. Higgs's journey is a perfect example of how science works. It's all about testing, refining, and evolving theories over time. What once seemed like wild ideas became the building blocks for understanding fundamental forces. Who would have thought that just hanging in there could lead to groundbreaking discoveries? The Higgs field is like a cosmic blanket, stretching across the universe and allowing particles to interact in unique ways, determining their mass based on how tightly they're coupled. This clever little trick helps in unifying electromagnetism and the weak force, and it shows how everything is interconnected. Isn't that just wild? Now, let's talk about symmetry breaking. It's a crucial concept in physics, akin to balancing a pencil on its tip. Any tiny disturbance leads to particles like W and Z bosons acquiring mass. It's a little chaotic, but super important for understanding how our universe works. When the Higgs boson was finally discovered at the Large Hadron Collider, it wasn't just a win for one theory, it validated the whole Higgs mechanism. This meant the predictions weren't just empty words, they were solid truths, reinforcing the foundation of the standard model of particle physics. So satisfying, right? But the world of theoretical physicists is not just sunshine and rainbows, it comes with its share of rivalry and competition. However, this fierce spirit led to mutual respect over time, showcasing how collaboration is key in breaking scientific barriers. This camaraderie was crucial in developing the Higgs mechanism, proving that teamwork can lead to magical breakthroughs. And let's not forget about the contributions from big names like Schwinger and Nambu. These physicists played a major role in refining the understanding of spontaneous symmetry breaking, setting the stage for future theories in particle physics. Their insights were like puzzle pieces that helped complete the picture of the Standard Model. Despite all the excitement, the acceptance of the Higgs mechanism didn't come easy. It faced skepticism at first, but as experimental evidence piled up, the tides began to turn, leading up to that monumental discovery in 2012. This journey really highlights the patience and intricacies of scientific progress. Who knew the road to discovery could be so twisty? In the early days, there was a buzzing debate about whether the Higgs boson was a lone ranger or part of a larger family of particles. This discussion really brought to light the complicated nature of predictions made by the Standard Model. Science is like a never-ending story, doesn't it? As the Large Hadron Collider roared to life, excitement filled the air, but there were lingering concerns about the clarity of the data. Scientists were cautious, knowing the potential for alternative explanations. This kind of meticulous skepticism is the backbone of scientific culture, keeping everyone on their toes. The intense scrutiny surrounding the Higgs boson sparked a wave of exploration into alternative models and even deeper questions in physics. This ongoing inquiry illustrates the dynamic nature of scientific understanding, pushing us to constantly rethink and reevaluate what we think we know. The LHC's High Luminosity project is a big deal. It's focused on increasing collision rates to further unravel the mysteries of the Higgs boson and its properties. But this upgrade comes with its own set of engineering challenges that will test the limits of what we can achieve in particle physics. CERN has really shown what international collaboration looks like. Against a backdrop of skepticism and logistical obstacles, they've achieved truly remarkable scientific outcomes. This teamwork has redefined modern particle physics and set a fantastic example for future scientific ventures. But the impact of the LHC goes beyond just particle physics. It's also leading to breakthroughs in other fields like medical imaging and computing. Talk about an unexpected bonus. This highlights how advancements in one area can ripple out and benefit society as a whole. The Large Hadron Collider, LHC, stands for humanity's relentless quest to test the very laws of physics. With each collision, it unveils profound truths about the nature of our universe. Its construction is a testament to what can be achieved through international efforts and cutting-edge technology. Makes you feel proud to be part of this human story, doesn't it? At CERN, the principles of openness and collaboration guide scientists as they sift through heaps of data, striving to reveal the universe's fundamental workings. It's this collective effort that fuels a shared journey towards advancing human knowledge, and it's super inspiring. Even with all the challenges faced, the legacy of the LHC is bound to spark future scientific adventures. It reinforces the importance of curiosity and the relentless pursuit of knowledge, driving scientists to delve into the unknown and explore new frontiers in physics. This rush to learn and discover at CERN blends the fields of engineering and physics, creating a buzzing community of idea exchange between global researchers. It's this collaboration that fosters innovative solutions to the complex challenges we face in science, showing that sometimes teamwork is the secret ingredient to success. High-energy collisions do more than just confirm existing theories. They ignite fresh questions about dark matter and other fundamental enigmas. These new inquiries propel us to advance our understanding of the universe, driving an endless quest for knowledge. Now, here's something daring. As particle colliders like the LHC churn out massive amounts of data, handling and analyzing all that information becomes a wild ride. Enter advanced algorithms and machine learning, which have become crucial in sifting through noise to find the golden nuggets of insight. Technology, am I right? The innovative methods developed for managing large-scale data in high-energy physics have crossed over into multiple disciplines, boosting efficiency and enhancing data sharing. It's like what we learn in one corner of science benefits the whole playground. Science truly is interconnected. Striking the right balance between data transparency and safeguarding sensitive analyses is crucial. Public data releases can unlock new insights while ensuring the integrity of research. It's a dance of revealing and protecting knowledge, and it takes finesse to get it just right. The process of analyzing data often leads to a refinement of theories, guiding future experiments based on successes and unexpected results. This iterative loop is vital for keeping the scientific engine running, ensuring that we keep learning and evolving. The statistical nature of particle physics means that even the rarest events pop up frequently in massive datasets, leading to both incredible discoveries and some face-bomb moments. This back and forth is essential for the growth of the field, teaching us valuable lessons along the way. Despite the standard model's successes, everyone knows it's not the whole story. This realization has scientists proposing extensions to explain pesky phenomena like dark matter. Unfortunately, these inquiries can stretch on for years without guaranteed results. It's kind of like waiting for your favorite show's next season. Back on July 4th, 2012, the announcement of the Higgs boson was nothing short of a blockbuster event. It wrapped up years of research and collaboration, reigniting interest in fundamental science. It's like the spark that lit a fire of enthusiasm for inquiry. Following that announcement, public interest in particle physics skyrocketed. People became eager to learn about the standard model and the significance of fundamental particles. Educators seized the moment, using this buzz to engage students in the wonders of science. That announcement wasn't just about confirming a theory, it represented a milestone for international collaboration. Scientists from all around the globe banded together, overcoming engineering challenges and pooling resources to reach this monumental discovery. It's a perfect example of how teamwork can change the game. Even with the Higgs boson officially on the map, scientists kept their minds open to the possibility of finding new physics beyond the standard model. The quest for understanding never stops, and ongoing research and data analysis mean there are always more mysteries to unravel. The Higgs boson, clocking in at about 125 GeV, was like the final puzzle piece in the standard model, confirming predictions and boosting confidence in particle physics overall. This discovery tackled key questions about particle mass and stability, igniting a wave of excitement in the scientific community. The Large Hadron Collider, LHC, stands as a beacon of international collaboration in science, gathering expertise and resources from all corners of the globe to achieve breakthroughs in fundamental physics. This partnership serves as an inspiring model for tackling global challenges through coordinated research efforts. Together, we can achieve amazing things. The implications of finding the Higgs boson go far beyond the physics lab. They've inspired a surge of public interest and education in science. The buzz surrounding the discovery emphasizes the crucial role of fundamental research in shaping cultural perceptions of reality. We're talking about a seismic shift in how we view the universe. The Higgs boson discovery sparked excitement among scientists and the public alike, leading to a whirlwind of media buzz about particle physics. However, many were left grappling with understanding what it all really meant, beyond just being a cool scientific breakthrough. It was a fascinating mix of awe and confusion. Post-discovery, researchers went into full-on detective mode, working hard to refine measurements of the Higgs particle's properties, like mass and decay channels. The goal? Ensuring everything lined up with theoretical predictions. This kind of meticulous analysis is what helps validate the standard model and keep the scientific community thriving. Now, let's address a bit of a controversy. The term God particle was thrown around, prompting debates within the scientific community. Some argue it misrepresents the Higgs boson and could lead to misconceptions about its significance. Even so, It managed to spark public curiosity about fundamental physics, so it's a double-edged sword. Pop culture loves to shape scientific discoveries into catchy labels, but sometimes this can obscure the real complexities of the topic. This phenomenon often overshadows the nuanced discussions that are essential for true understanding. It's a classic case of simplifying science a bit too much. The Nobel Prize awarded for the Higgs boson discovery triggered debates about recognition in the scientific world. It underlined how collaborative modern research has become while highlighting the limits of traditional awards. In a field driven by teamwork, it's a great reminder that every contribution counts. Yet even with the Higgs boson now a part of the scientific canon, big questions about dark matter and gravity still loom large. It's a reminder that gaps in our understanding remain, and there's still a lot of detective work to be done in the universe. The mystery of neutrino mass is still a puzzler, since the simplest Higgs mechanism can't quite explain it all. This push for clarity has led to proposals for additional components that might shed light on the situation. It's a classic case of needing more pieces to complete the puzzle. On the other hand, the matter-antimatter imbalance presents another conundrum. Observations show a dominance of matter, even though we expected both matter and antimatter to be produced in equal amounts in the early universe. It's a real head-scratcher, adding more intrigue to the cosmic story. And then there's the hierarchy problem. Why is the Higgs boson mass so low compared to the Planck scale? This question has huge implications for understanding fundamental forces and might hint at new physics waiting to be discovered. It's one of those puzzles that keeps physicists up at night. Enter the composite Higgs models. These propose that the Higgs boson might actually be a bound state of more fundamental particles, similar to how protons and neutrons are made up of quarks. This theory aims to tackle the hierarchy problem in particle physics, and it's definitely one to watch. Grand unified theories are like the ambitious dreamers of physics, suggesting that all fundamental forces could unify at high energies. This could introduce new heavy particles and multiple Higgs fields. But here's the catch. There's a lack of definitive evidence for these theories, leaving many questions wide open. It's exciting yet frustrating. For neutrinos, exciting extensions like the seesaw mechanism are in the spotlight. They aim to explain the small masses of neutrinos and their role in the universe's matter-antimatter imbalance. However, these theories often demand experimental validation that's currently a tough nut to crack. Current measurements indicate that the Higgs boson interacts with other particles just as the standard model predicts, confirming that we're on the right track. However, precision has its limits. This opens up the door to the possibility of anomalies waiting to be uncovered. Who knows what surprises lie around the corner? Some speculate that the Higgs boson might be part of an even more intricate structure involving heavier states or hidden particles. Future experiments could unearth these possibilities and unveil deeper insights into its nature. It's a thrilling prospect that keeps scientists eagerly anticipating what's next. In the end, the journey into the realm of particle physics is a wild ride full of twists and turns. From groundbreaking discoveries to lingering questions, it's clear that the quest for knowledge is far from over. So, buckle up, because the adventure is just beginning.